When RAG first came out, everybody was chunking by word, then by sentence, and then by paragraph. And it only took until recently people started chunking by concept, by semantics, right? And so what we're going to talk about today is the ability to chunk by any arbitrary characteristic of any file type. Videos, image, audio, documents. This is the multimodal way to build indexes that are inclusive of the exact characteristics you want when you build retrieval systems. So if we think about chunking strategies, really the question is, okay, why do you need to chunk? Well, it's important to chunk because A, encoder models have a limited context window, and B, you have results that you need to ensure are the most relevant for your LLMs to do their reasoning. LLMs are only getting better and better, and when we say better and better, we mean that the reasoning capability is only improving over time, right? But the reasoning is limited to the concepts, the content that you're giving it, right? And so this is why it's important to have very good chunking strategies so that you ensure that your LLM is not getting overwhelmed by data that's not relevant to the query, right? And so, for example, a lot of embedding models have between 512 and around 8,000 token limit. And so we want to be very precise with what we want to encode in these models. And again, there are different chunks that have different results when we actually run the retrieval operation. And again, your chunking isn't just limited to text. We can chunk by figures, graphs, tables, charts, headers, footers, and PDFs. You can chunk by time, scenes, shots, keyframes, faces in a video, or you can chunk by speakers in an audio file, the duration, the silence intervals, etc. So if we think about different types of chunking strategies, let's just go down the list. In text/PDF chunking strategies, you have really with any of these modalities, you have a fixed interval, right? So chunk by every n tokens, every 100 tokens, and there's typically some kind of overlap that you want to specify, or you want to do sentence-based chunking. So every time there's a period, that's a chunk, and we can reasonably believe that's an independent thought. And so those are often pretty useful for capturing thought-based embeddings. But then we get into more interesting and powerful chunking strategies such as semantic-based chunking. And so what this means is, let's say we were to encode every sentence. Ethan likes dogs, dogs like Ethan, right? These are two different sentences, and we were to encode them all individually. And then what we do is we measure the similarity, right? Using cosine similarity, we measure the similarity between these two different sentences encoded in vector space. And then if the distance between them is around a certain relevance threshold or below a certain relevance threshold, that's a chunk delimitation, right? That's a boundary in the chunk interval, right? And so we can use semantic-based chunking to determine the conceptual differences between a corpus, right? A corpus can be text, can be video, can be image, can be whatever. And again, if we have a PDF, we can chunk by the different structural elements of that PDF. The layout, the headers, the footers, the tables, charts, graphs, whatever. So in videos, again, just like any other modality, we have splitting by time, right? Every 30 seconds split by, or capture this embedding, right? We can split by scene. Given a certain, as the scenes transition, we can use models like PySceneDetect or AutoShot, which are open source, to measure the pixel differences between every frame. And as the pixel differences increase, we can reasonably believe that is a new scene, right? And so that's how we do scene chunking. And again, we can specify different thresholds, etc. Shot boundaries, right? Is the camera positioning of the video different? That's a shot boundary. That's a new chunk, right? Keyframe sampling. So all of these are different methods of chunking videos. And this isn't conclusive. There are tons of other methods like using models like SAM2 to chunk by objects, right? And so this allows us to actually capture all of the scenes that a particular object is in, and that is an independent chunk in our index, right? And audio allows us to do the same kind of, within an audio file, we can chunk by similar kinds of ideas, right? Fixed duration, every 30 seconds chunk the audio and maybe encode the audio, maybe transcribe it, whatever. We can also determine the activity, or we can do speaker diarization. So what that means is every individual voice that is speaking, we can chunk by those unique characteristics, those unique voices. And so if we think about chunking, chunking isn't just, hey, this is some kind of fixed delimitation, this is some kind of boundary. We can specify the overlap of the chunks, right? And so as you can see here, as we change the overlap percentage, we can say, hey, between every different chunk in our from our corpus, as we go through the chunking processing, we can specify what sort of overlap we want to have. And a 50% overlap in this case would be the highest, and a no overlap would be the lowest. And it's important to have overlap, or given your use case, because it allows you to actually capture the kind of different elements in the preceding and afterwards chunk. So it gives you this kind of like concept of a safety net if we've lost some chunks in our chunk processing. Right, and so we have different trade-offs for how we do chunking, and it's important to actually measure your index and your retrieval accuracy against these trade-offs. So for example, if we have lower chunk size, maybe we have very precise results, but we could be missing a lot of things. And so as we go higher and higher in the chunk size, as you can see, precision lowers, right? So are we getting the exact results that we want? Is the LLM reasoning about the exact data that it needs, or is context being preserved, right? So we are preserving a lot of context at the trade-off of maybe potentially overwhelming or not having as many documents that are capturing exactly what we're looking for. So if we look at, in the mixed-peak documentation, think of the object decomposition as these are different ways of chunking sources, right? So in this case, our video has scenes. Within the scenes, we have faces. Within the faces, we have expressions, right? We are chunking by each of the preceding steps as we go further and further down the tree. And so if we were to build out this exact kind of object decomposition workflow, let's say we're going to create a collection, and in mixed-peak, when we create a collection, we can use other collections as sources, or we can use raw buckets. So in this case, we'll use this raw bucket, and this raw bucket has, let's say this raw bucket has a video, I believe. Yeah, creative asset URL is a video. So we'll select this as the source, and we'll begin building our object decomposition flow. And so what we could do is we could start with time as the segmentation. So we could say, hey, every 30 seconds, and this is entirely dependent on the data that you have. And so for example, if you have very large videos, then maybe you want to split initially by 30 seconds, or if you have very small videos, maybe you want to just split by scene initially. We'll just assume this video collection in this bucket is quite large. We'll say they're 5-10 minutes each. And so we'll split each video by 30-second intervals. And we will use the creative asset URL as the source for this multimodal extractor. And we'll call this time segments, right? And so then we'll send the results of that to two other different feature extractors in parallel, right? So we'll create another multimodal extractor down here. And this other multimodal extractor will say, we'll split by, call it a scene segments collection. And we'll use the output of that previous collection as the input for this one. And so they tend to, each of these multimodal extractors spits out a source, or a video segment URL. And so this is the segment from that collection. And what we'll do here is we will use scene as the split interval. And if we actually go into the documentation, we can see the different split methods that are available: time, scene, silence, etc. And these each have their own parameters. So if we say video splitting, so time has time split interval as a parameter, defaults to 10. Scene has a detection threshold, so that's 0 to 1. And then silence has a silence detection, or a silence threshold. So these are the different thresholds that determine the boundary of the chunk for a video. Well, we can do the same thing for image, but we'll just do video for this example. And so again, we're going through the videos. Every time we upload a video, we process it through this object decomposition flow. And the very first stage is splitting by time. And in this case, we are splitting by 30-second intervals. And then the output of that split by scene. And we'll just do the default 0.5 here. And then do the same thing with this other, in parallel, do a time, or I say silence detection. Silence segments. And then again, we'll be using the video segment URL from the time segments collection, which is right here, the time segments collection. And we can choose to enable transcription. We can generate embeddings. For any of these multimodal extractors, we can generate a description. We can generate transcriptions, transcription embeddings. We can do OCR, or we can even customize how we want the response to look like. So we could say we wanted to have these JSON properties, maybe certain keys that we want to use for our retrieval operation down the line. And so if we were to create this collection, or these this pipeline here, oh, it already exists. So this time segments collection already exists, as we can see. So if we were to then build a retriever pipeline, that retriever pipeline can then traverse each of these collections independently. So we'll say this is a multi-collection traversal. And we're going to do text segments, we'll do scene segments, and we'll do time segments. And so each of these, and we'll just do a text query, but we can do an image query as well. Anything, we can support any kind of schema as the input for these retriever operations. We'll say text here. And so now what we'll do is we'll just provide an input here for an example, and then we'll create a feature search stage here. And what we can do is see the different types of feature URIs that we have available. In this case, the text embeddings collection is using this feature URI. We'll use it here. We'll say collection identifiers, and then it's just an array of strings. So text embeddings is one. So we'll just say text embeddings here, and we'll use that feature URI. And so if we run that, it is running that dog input through this encoding model, and it's doing a feature search on the documents in this collection. But we can do multiple collections as the collection identifier. And so what this is doing is it's doing a feature search across all of the collections that support these feature URIs. But in this case, only one of them has that. Only one of the collections has that. I know two of them have the vertex multimodal embedding. So this is using the vertex. This is using the vertex encoding model. So we'll see time segments here, time segments, as well as scene segments. And so again, this is going to run the dog query across both of those collections, assuming both of those collections has the multimodal, vertex multimodal embedding feature URI. But what we can also do is not only do a single feature search, we can do searches. So we can copy this and run multiple. We can do a hybrid search across multiple collections or collection identifiers or feature URIs. So we could say, hey, this feature URI. Cool. And so what this is doing is it's saying whenever I execute this retriever, run this dog input, this dog string, through the retriever pipeline, right? And so we're just using a variable. And this is just for testing, right? When you operate an actual retriever, you will be supplying input schemas on demand. Or if you're using taxonomies, you would use different documents as inputs for your retriever. And so in this case, dog is getting provided to both of these stages. And then what we'll probably be doing is using the reciprocal rank fusion. See where that is being used. We would be using the RRF fusion technique to basically just combine the ranking of the different results across these different feature URIs. And again, feature URIs under the hood are really just indexes plus encoder models. And so they're very tightly coupled. Oh, so we gotta do a feature URI here. Let's see. Oh, we got to use a different fusing method here. But what we can say is the ability to actually traverse different collections in our retrieval operation gives us the recomposition that we talked about in a previous video. And so again, recomposition is we take all of the collections that we've decomposed from the object and we recompose them on query time. So product demo with Sarah can say, hey, product demo is the scene collection. Sarah is the face collection. Do a retrieval operation that spans all of them in one single execution. And so the sky's really the limit on what sort of characteristics you can chunk from an object. Objects can be videos, images, audio, documents, can be whatever. And we can chunk by any arbitrary characteristic. And once we can chunk by these characteristics, we can decompose them. And once we decompose them, we can reassemble them on retrieval time to get exactly what we want with the highest level of precision and the highest level of recall across our multimodal data sets. Thank you.